Hello, everyone. My name is Buğra Özdemir. I am the image data specialist at Euro-BioImaging, and my talk will be about our own contributions to the tool development around the cloud-optimized file format OME-Zarr. But before diving into our own contributions, a very short background about standard file formats. So perhaps the most popular file format until recently has been OME-TIFF. And this is partly because maybe partly owing to bioformats package that can read over 150 different proprietary file formats, and also partly owing to the OME-XML metadata, which has a rich representation of diverse metadata. And OME-TIFF, however, is becoming limiting, especially with large multidimensional data, such as this volume EM data shown here, which can easily reach terabyte scale. And because of the TIFF's plane-based access, the performance is really low with accessing such data, especially even if you just want to access a small subset of the data, you need to basically read the entire image array, and this is limiting, especially when the data is also located in an object store. To avoid these limitations, the next generation file formats are being developed, such as OME-Zarr. So these are basically dividing, like a splitting image array up along its different dimensions into smaller chunks, and each chunk is saved to a different file. And when the user accesses a small subset of the data, only those chunks corresponding to that subset are loaded. This dramatically improves the access performance, especially when the data is remotely stored. And in addition to the chunking, NGFFs are also natively multi-scaled, so there are multiple resolution levels making up an image pyramid. And when the user is viewing the entire image, the libraries basically bring the lower resolution layers of the pyramid, and when the user zooms into a specific subset of the image, then the libraries switch to the higher resolution layers, somehow keeping the amount of loaded data at a specific level. In addition to these performance-related aspects, the OME-NGFF also offers a common layout for storing data, metadata, and derived data, such as segmentation masks. And basically, a single series is a file hierarchy, as you see on the right-hand side. And there are multiple metadata files at different directories representing what is stored at that particular directory. If there are segmentation masks, they go under the label subdirectory, and it's also possible to store image analysis results for particular labels, and also some display metadata, for example, in the same hierarchy. So if you want to learn more about the specifications, you can visit this tiny URL, which will lead you to the specifications web page, which is constantly getting updated. Nowadays, also different data types, such as annotations and polygons, are also being integrated with OME-Zarr specifications. And you can also learn more about, learn about the performance comparison between OME-Zarr and other file formats. You can see this publication. And also, if you want to learn more about recent tooling and such as converters, viewers, libraries, you can also have a look at this recent preprint. So when we come to our own contributions, first, I would like you to have a look at this diagram on the right-hand side. So this is an oversimplified representation of the life cycle of OME-Zarr data. So after being acquired, the data must be converted into OME-Zarr, because so far no microscope is directly generating OME-Zarr data. And there are already a bunch of converters that can be used for this purpose. And after the conversion into OME-Zarr data, it can be basically submitted to an archive. And ideally, like afterwards, other researchers will pull this OME-Zarr data from the archive for reuse, for example, for de novo image analysis. And the results can be then integrated back with the OME-Zarr data and perhaps like submitted again to another archive or to the same. So this already is quite a complex process, like a workflow that already uses a number of like different clients, libraries, web services. So therefore, I think, so we decided to use a workflow management system when we started working on our own tool, which basically covers the parts, the processes shown in red arrows. So basically, we aim to develop a tool that's capable of control and parallelized conversion of batches of images into either of the standard image formats, OME-TIFF or OME-Zarr, can interact with remote locations such as biostudies, user space, or with an arbitrary S3 bucket. It will require minimal manual dependency management for the user, and also therefore provide incentives for more researchers to make their data available in OME-Zarr format. So when I said workflow management systems, basically we take advantage of these aspects of workflow management systems. So it is relatively more straightforward to parallelize workflows locally and also on compute clusters. The workflow saved to a format which is basically executable and shareable, and can be also like shared over workflow registries, such as Workflow Hub or like other registries specific for a particular workflow management system. And also dependency handling is relatively more straightforward. For example, dependencies can be containerized, and containerized can be led to interact with each other to construct workflows. And in our case, we are using Nextflow as part of our tool. Basically, the tool is named Batch Convert, and it can perform parallelized conversion, as I said earlier. And it has basically two types of conversion modes, either independent or grouped conversion, which I will explain later. And it is possible to select subsets of files using either pattern matching or wildcards. It is capable of running either via a Conda environment or via a Docker or Singularity container that we have on Docker Hub. And it can communicate with remote stores, as I said, S3 buckets or biostudies user space, and can also run on Slurm clusters. And we also provide interactive configuration of all these different processes. So this is an overview, therefore. So input and output, different input and output combinations, therefore, can be attempted. And like I said, the dependencies can be also acquired and run in either using containers or Conda environment. So what I meant with independent and grouped conversion. So independent conversion means each file in the input folder will be treated as a series. So each input then will be mapped to a single output. And the grouped conversion means the tool will try to identify a group of files that can belong to the same series. So in this case, for example, this these images here basically are belonging to the same series. So there are 2 channels and 3 time points, and they will be automatically recognized and concatenated along these axes into the same OME-Zarr or OME-TIFF, whichever is chosen by the user. So this can be specified by simply passing this merge files flag. So from this point on, I would like to show short videos to demonstrate some of those features that I described, starting with the interactive communication, to give you an idea what can be done with this tool. So first, the user may want to have their own conversion, like default conversion parameters for either OME-Zarr or like OME-TIFF conversion. So this can be done by simply entering batch convert, configure OME-Zarr, and then the user will be prompted to provide parameters. And for parameters that are like limited to certain options, these are also given, as you see, for example, downsampling algorithm that can be simply chosen from one of these. And that's it. And after this, these are basically the default parameters for OME-Zarr conversion. And this kind of interactive configuration is possible for remote stores. So the user will then simply provide credentials, URLs, whatever, and other conversion process, for example, for OME-TIFF, and also for Slurm parameters. And then this is a simple conversion of local data to OME-Zarr, OME-TIFF, sorry. These are the input files. So it also shows you the next flow process, convert each file to separate OME-TIFF, and the number of jobs being executed. So this is a workflow with just a single process. And here you see the output folder with OME-TIFF files. Then we can do something similar using singularity container if we don't have, for example, an Anaconda or Miniconda. Because, yeah, I forgot to say that by default it is using a Conda environment. So it is just creating a Conda environment at the first execution of the conversion. If the profile is not specified at all. Alternatively, you can specify the profile as singularity or Docker, then it will pull the Docker image from Docker Hub, which you will see now that it's actually telling us that is pulling the singularity image. It takes a while at the first execution, then the image is basically cached and used in the next executions. And then this is the output folder. So, as I said, profile Docker can also be used if you have the Docker instead of Singularity on your system. And then this is an example of like selecting a subset of files to convert. Pattern matching is typically used. As you see here, we have like 3 different groups of images with certain patterns, like D3 here, and then IG4 here, and then IG7 here. It is possible to select a subset of these images by simply passing pattern or P, and then the pattern itself, and then only those images will be selected and converted. Therefore, we have just 14 jobs. Alternatively, we can also specify which of those images are rejected from conversion rather than selecting. This can be done by passing reject pattern or RP, like you see here. So we are just rejecting all those files with this IG4 pattern. Then we have 22 jobs. So next, I would like to show an example of grouped conversion. I'm using the same files for this example. In this case, there are basically, so when we simply specify the merge files flag, then it is performing a group conversion. And as you see, it uses two processes. First, it creates a pattern file to recognize different groups, in this case, 3 groups, and then it performs this other process like concatenate to single OME-Zarr. This means 3 jobs are executed in parallel. So parallel processing is also supported, but this time along different groups. And the output is basically also indicating the ranges along which the concatenation took place. So this is for the first pattern, and this is for the second one, and so on. And now I will show an example of interacting with a remote location. This is achieved by specifying the source type and destination type. And the values can be like local, S3, or BIA for biostudies. So the first step is, of course, again, configuring the remote location. In this case, I'm just skipping because for me it was already configured. And then it is important to have pay attention to the bucket name, because once the configuration is done and once the source type is specified as S3, then the path will be relative to the S3 bucket. So bucket name does not need to be provided again in the command line. Then I used the Minayo client basically to look at the FAIR workshop folder in my S3 bucket, which contains this JPEGs folder. Some JPEG files. And then I execute the conversion, specifying the source type as S3 and also destination type as S3, so that the output will be pushed again to the S3 bucket. So this is this can be also like combined with, for example, pattern matching or grouping, and so all these different options that I showed earlier. Then basically we have these results in the same FAIR workshop folder, and also the OME-TIFFs, as you see. Then here in this example, I would like to combine the merging, like group conversion again. But here I would like to also mention that it is possible for the user to specify, like impose the axis along which the files are concatenated. In this case, I use those JPEGs again, and JPEGs basically don't have any metadata specifying any axis. And also in our case, in this example, there is no information of access in the file names. Therefore, the user can basically specify the concatenation order. And in this case, it is time. Therefore, we simply pass time in front of the concatenation order, and then it will concatenate the data along the time dimension and push it back to the S3 bucket. So there is only one group. Therefore, there is only one job executed. And this kind of concatenation is also possible along multiple dimensions. Then we also have this grouped OME-Zarr pushed back to the S3 bucket. And in the last example, I would like to also show a visualization of this example, so that we have now an OME-Zarr concatenated along the time dimension, and we would like to just visualize this. Then we can simply use the Napari package for this. So using the Napari OME-Zarr plugin, and then here you see the data is streamed from the S3 bucket. So first, it has some interruptions, but then it becomes a fluent movie after some seconds. So it's like this. So one important point is that in order to execute a command like this, the bucket should be public. So I think there is some way to work around doing this also with private buckets, but it's not possible to directly just pass this visualization line. So I guess that's it from my side, and thank you very much for listening.